All right, so it's a pleasure to have Claudia Landi from University of Modena and Reggio Emilia, who will be talking about multi-parameter persistence from the viewpoint of discrete Morse theory.
Well, thank you, Facundo, for the introduction, and many thanks to all the organizers for having me talking here. Yes, today I'm presenting some recent and less recent works of mine, trying to connect the theory of multi-parameter persistence with the discrete Morse theory. And so now the slide doesn't move, but okay, I think I can do it like this. So I'll give a brief introduction to persistence, not because this audience doesn't know about persistence, but just to explain why I think I'm looking at a different side of multi-parameter persistence than is more usual. And indeed, I want to consider persistence preserving discrete gradients. And especially, of course, the most important ingredient in discrete gradients are their critical cells. And I'll try to explain why I think that they are usual for visualization purposes, for fibering persistence modules, and to get Morse inequalities of persistence. So, I'm sorry, I have this problem with my keyboard, doesn't work the keyboard. Okay, so a brief introduction of persistence. This is the usual pipeline of a persistent homology, for persistent homology, where one has a cell complex sigma endowed with the function, and then one takes the sublevel sets of the function. They form a filtration in the sense that these sublevel sets are nested one into the other as the parameter u, real parameter u, increases, and then one applies a homology and one gets the persistence module M, which can be seen as an algebraic object in itself, and so we may forget where we got it from, and it has its own algebraic properties, so that we can apply, for example, commutative algebra or results from quiver representation theory, and from those theories one obtains a decomposition of the persistence module M into indecomposables that in the one parameter case are interval modules. They are called interval modules because their support is a real interval with endpoints bi, di, and these intervals then can be grouped together to form the barcode of the persistence module. And of course, can you see the bottom of my slides, or are they covered by the, okay. And of course, because of this, in this setting, because the indecomposables are really interval modules, we have this equivalence between the invariants we find with the decompositions and the barcodes. But on the other hand, the barcodes can be found also applying Morse theory. If the function f is a Morse, the endpoints are B, B, and D, di and di are critical values of the function corresponding to critical points that are paired by following the gradient of the function. And so there, the theory is also rooted in Morse theory. On the other hand, when we move to multi-parameter persistence, the picture, the story is pretty much the same, except that perhaps here the inequality here that we use for building the filtration is simply the partial order that we get using the usual real order on each component of the function f, which now takes values in Rn. And so there are classical theorems from commutative algebra that again guarantee the decomposition, but unfortunately the decomposables are not of a simple shape. We can't guarantee that they have a simple shape, or at least, or even only one shape, and so it is difficult to connect this decomposition that comes from commutative algebra with the Morse theory. On the other hand, one can still define barcodes. These times they are barcodes that one obtains by slicing the persistence module M along lines. But these are weaker invariants. So the invariants that we get from the decompositions are not equivalent to the invariants we get by slicing the persistence module along lines. I will describe more in detail later how we get them. On the other hand, so the former are stronger invariants, are complete. Indeed, the latter are not. But I will focus on this side of the story, because I think it is possible in this case to put multi-parameter persistence in connection with discrete Morse theory. So to do so, we need to define discrete gradients, and in particular persistence preserving discrete gradients. So as I mentioned, the setting is the one where we have a cell complex, for example, a simplicial complex, and we have a function defined on the simplices of the simplicial complex, taking values in Rn, and we can form the subcomplexes containing only those cells that have a value by the function f that doesn't exceed u in this partial order that we have on Rn, and these subcomplexes are nested. And one way to define such a function f that has these properties is the following. If, for example, we start from a function defined on the vertices of a simplicial complex, so we only have the data on the vertices of the simplicial complex, then we can extend the function to all other simplices just by taking the maximum of the value of each component of the function f on the vertices of the simplices. So for example, here we get 2, 1, as 2 is the maximum between 2 and 0, and 1 is the maximum between 0 and 1. And in this way, we can extend the data to all the simplices, and then, as I said, we can construct the persistence module of this pair given by the simplicial complex and the function. Now, if we want to if we want to consider apply a discrete Morse theory to this setting, first we need to define what a compatible discrete gradient is. In general, a discrete gradient is something very classical that that consists in partitioning the simplices into two sets. There are simplices that are singletons, so they are not paired, and there are other simplices that form pairs, and it can be so only when one is a coface of dimension one more than its space. So, for example, tau is a coface of dimension one more than sigma. In this case, the pair is represented by an arrow, and simplices from which an arrow neither starts nor ends are the critical simplices, the singletons. So in this example, the colored simplices are critical, the rest are paired simplices. And we also, in order for this vector field to be a gradient, we also need that the vector field is acyclic, so that this means that we can't form a closed path following the gradient. And what does it mean that this gradient is compatible with the function defined on the simplicial complex? It means that whenever the gradient pairs two simplices, then the function must have the same value on those two simplices. This guarantees that all arrows remain inside the same sub-level set complex. And it is guaranteed that if we collapse a simplicial complex using the collapse induced by a gradient which is compatible with the function f, the Morse complex that we get is isomorphic to the persistence module we started of the pair sigma f. And so working on the Morse complex, which is the complex consisting only of critical cells, is the same as working on the original complex, and therefore one wants to build gradient vector fields that have the minimum possible number of critical cells. And one way of doing this is available, for example, for simplicial complexes. If we start from this simplicial complex with this function defined first on the vertices and then extended to the other simplices by taking the maximum component by component, then we can build a gradient on it, which is compatible simply by first organizing, indexing the vertices in such a way that the order we had on the origin for f is linearized, and then extending again to other simplices by taking the maximum. And now we can work on this simply even in parallel, vertex by vertex, taking their lower star, and their lower star can be further partitioned so that in each partition of the lower star of a vertex, we simply apply homotopy expansion. And in this way, we can build a discrete gradient compatible with the generic f in linear time on the number of vertices. And this, the gradient we get is even guaranteed to be persistence perfect, which means that the critical cells, we have critical cells exactly where persistence changes. at values where persistent changes and they are in the correct number. And this is guaranteed for two-dimensional simplicial complexes and three-dimensional cubical complexes. So we know how to build discrete gradients that are compatible and optimal. Now, what can we do with these gradients? First of all, we can use them for visualization purposes. For example, here, this is a slice of a data set representing the temperature and pressure values on a cubical grid describing the Hurricane Isabel. And as you see, the two gradients, the temperature gradient here and the pressure gradient here, are not agree everywhere. There are places where they strongly disagree. And we study these two gradients together, and we using the previous, we computed the combined gradient, and we computed the critical cells. And if we cluster the voxels by taking the number, so we say that the two voxels belong to the same cluster if they belong to the same critical component of critical cells, and we consider clusters with more than 10, 100, 400, 2000 critical cells, where the color encodes the number of voxels in the cluster. Then we see that we can visualize very well the part of the data where the two gradients disagree, and which is exactly the eye of the hurricane. From more theoretical reasons, we can use critical cells to fiber M, the persistence module M. So I go back and I take a filtered simplicial complex. And all of this is shown for 2 parameters, but this is general. It can work with n parameters, and now we slice. So from this filtration we can get a persistence module which can be sliced. Slicing the persistence module means that we restrict the persistence module to a line L, such as, for example, the orange line, which needs to be increasing. In 2D, we may say it has positive slope. In ND, it is an increasing line. And we restrict the persistence module to this line. And in this way, the persistence module becomes a 1-parameter persistence module. And so it is decomposable into bars, into interval modules. And for example, the blue bars are the bars for this line. And we can repeat this for every increasing line. And what we get is the so-called fibered barcodes. It has also other names, but one is the fibered barcode. And this is a way for visualizing the persistence module, but of course the drawback is that there are m² lines to consider, where m is the number of simplices, and when we want to compute this barcode, fibered barcode, we need to recompute persistence for every line. So we perform the same computations and reductions many times. So one idea that was already present in a paper by Lesnick and Wright, for example, is that of looking for barcode templates, and they use Betty tables to do that. and here the proposal is to use critical values of critical cells. So again, I assume that the simplicial complex is endowed with the compatible gradient vector field, and the critical values are the entrance time of critical cells, for example, this yellow instance. And also we take the least upper bound of these critical values. And what we will see is that these four grades of the filtrations are the relevant one, because what happens outside that doesn't make any difference, as everything collapses to the critical cells. In particular, we can define an equivalence relation between lines as follows. Two lines, L and L prime, are equivalent if they are in the same reciprocal position with the points of C bar, the closure of critical values, which means in 2D, being in the same reciprocal position means that L and L prime leave the same points to their left or to their right. They are always lines with the positive slope. And so, for example, L second is not equivalent to L, and not equivalent also to L prime, because C2 is not in the same reciprocal position. But this equivalence relation can be defined for any number of parameters. We just need to check which face of the positive cone of the boundary of the positive cone of a critical value is hit by a line. If two lines hit the boundary of the positive cone of each critical value in the same phase, then they are equivalent. If not, because they are hitting on different faces, then they are not equivalent. And equivalent lines are important because not equivalence line. This equivalence relation is important because a barcode of restrictions along equivalent lines are in bijection, which means the following. So assume that for L, the fibered barcode has a bar like this one, then we can, without recomputing the barcode, we can infer what is the barcode on L prime simply as follows. For this endpoint, we first pull it to the greatest critical value before it, and then we push. So we pull it there and we push it back onto L prime. The same for C3. We pull it to the greatest critical value below C3, and then we pull back. We push back here, and so we get these 2 points, and we know that the bar here is this one. So in this way, we don't need to compute the barcode along every line using the standard persistence algorithm, which takes cubic time for each line, but it is sufficient to compute the barcode along representative lines. And to do so, we just need to know which lines are in the same equivalence relation class with respect to the critical values. And another situation where critical cells turn out to be interesting if one tries to build Morse inequalities for persistence. We have in this case, U is fixed, And we take the chain complex known as the Koszul complex of the homology of the sublevel set under U. And in the case when we have only two parameters, this means that we take U minus E1, U minus E2, and U minus E1 minus E2. Here I am assuming that the function f, for simplicity, I'm assuming that the function f takes value in the integer grid, but because everything is a discrete, finite simplicial complex, this is not restrictive. And now we consider the sublevel set for these 4 points, where this is the important point, the reference point. And we consider the maps induced by the inclusion for these maps. And from this, we can build this chain complex, which is called the Koszul complex, where the first map is from here to the direct sum of what I have here and what I have here. And this is called the split map. And this one, the merge map, simply merges this map with this map using so from the direct sum of what I have here and here to what I have here. And this is a chain complex and can be constructed for any number of parameters. And because it is a chain complex, we can take its homology, and its homology, the dimension of its homology are called the Betti tables. So for example, I use this notation xi qi, where the superscript simply reminds me that I am studying a Q homology of the simplicial complex. And whereas the subscript reminds me if I am considering a homology of the Koszul complex in degree 0, in degree 1, or in degree 2, or in general in degree n. And so, for example, okay, can you see? Sorry. Okay, I hope you can see. No. And so, for example, if I have this simplicial complex filtered in this way, this simplicial complex filtered in this way, we take H0. For example, we study the connected components, we get this persistence module M. And now if we study the Betti tables, we get, so on top I have 0 because I'm studying H0. So this is not very interesting. What is interesting is here. This is what I have, the zeros homology, dimension of zeros homology of the Koszul complex, of one homology, of two homology of the Koszul complex. And what do these tables tell me? Well, psi 0 basically tells me where there is a birth, because it corresponds to the dimension of a cocker, and so tells me when something new appears. And we can see that something new appears only here and here, which means that there is this entrance of this vertex and the entrance of this vertex, whereas psi 2 for example, tells me that it is non-trivial only there, and which is here. And why is it so? Because it is the kernel of the split map. So it tells me that when I move here and here, I get something that goes to 0, that belongs to the kernel of the sum of these maps. And so Psi2 tells me that there is a death in 2 directions, whereas Psi1 tells me that there is a death only in 1 direction. So, for example, this one is a death in this direction, or this one is a death in this direction. So they are linked to birth and death, but in a different way than in one parameter persistence. But what is interesting is that it is possible to derive Morse inequalities, because the Koszul complex is a chain complex, and so we can find strong Morse inequalities for that chain complex. And these Morse inequalities involve, on the one hand, the dimension of the homology of the chain complex. That's the right-hand side of this inequality. And on the other hand, they involve the number of critical cells that enter the filtration at a certain instant, at a certain location. From the strong Morse inequalities, we can, as usual, get weak Morse inequalities that tell me that the number of critical cells that enter the filtration at the instant at the value u is bounded from below by the Betti tables, or vice versa. The Betti tables are bounded from above by the number of critical cells. But these inequalities here, derived from here, are not very interesting, because you see there is no alternating sign here. There is something positive, the birth, minus all the deaths. And so very easily this gets to be negative, and so these inequalities are not very interesting, but they can be improved. And we get these inequalities that are sharp now, so they cannot be improved. At least they cannot be improved if we check what happens on a sphere. And indeed, we have a construction that works in any number of parameters that allows us to show that there is an equality between the number of cells that enter the filtration and the sum with the sign of the Betti tables. For example, if this is a U, this is my location U that I'm considering, here no cell enter at this position, but nonetheless there is one birth. So none cell enters, so the number of critical cells is 0. Of dimension 1 is 0. On the other hand, H1 has a birth, so this is 1, and Xi0 is 1, and there is no death, so this is 0, and this is 1. And this example can be reproduced for any number of parameters, and so this proves to us that we have got the sharp inequalities that we call sharp weak inequalities. So in conclusion, what I meant to tell you today is that the critical cells from discrete Morse theory capture diverse and fundamental aspects of a multi-parameter persistence. And there is more to discover. For example, I'm currently working with my collaborators on defining new distances for persistence modules or computing known distances for persistence modules based on the equivalence relation between lines that I have presented. And also I'm trying to describe more in detail the relationship between the support of critical values and the support of Betty tables. So I believe that they could coincide, at least in their when we take their closure with respect to the least upper bound, but I have not managed to prove that. I have managed to prove only one inclusion, not the other one. And so I don't know what the truth is about that. And so, as I said, this was based on many papers with many different collaborators, and here are listed all of them for reference. And I thank you very much for your kind attention.
Thank you, Claudia. I suggest we unmute ourselves and upload briefly. Are there any questions or comments for Claudia?
Hi, Claudia. Can I ask you a question? So just to make sure that I understood, when you mentioned that that you compared the way that you select lines for filtering with the work of Lesnick and Wright, do you get the same lines up to equivalent, the equivalence relation that you defined?
If I were able to prove that the support of the Betty tables is exactly the same as the support of critical cells, I could say that the equivalence that the representative lines are the same, but I'm not able. I have no experiments about that, and I have not this result. So I just wanted to say that the idea is more or less the same, only that they use Betty tables. We use only Xi0 and Xi1. Actually, they don't need all of them. We use critical cells. Also, another difference is that when our gradient is not perfect, we could have more values that we consider than they are actually needed, because if it is not perfect, there are critical cells that have that do not determine any topology change in the persistence change. So we might have more points. And the other difference with their work is that they do not define this equivalence relation, but they move to the dual space. So they work only in dimension 2 for 2 parameters, and they move to the dual space, and they take, so they do not explicitly define this equivalence relation. I should say that our method is general, but we have no implementation contrary to them. And also, even if any number, in theory, we could work with any number of parameters. In practice, we don't know how to determine to which are the equivalence classes. We have an algorithm only for 2 parameters. So these are the main differences.
Okay, clear. Thank you.
Claudia, maybe I have a question as well. So these critical cells, how stable are the positions of these critical cells when you change your function or complex?
Yes, I don't think the critical cells themselves, I don't think they are stable, because they are not even stable in one parameter. So if I take this one and this one, they might be very close to each other, F and G, but their maxima are maybe very far away from each other. It's on the other hand, I think that so the cell itself may be they may be very far from each other. I think that their values should be closer to each other. And this is also something I'd like, we would like to study together with Andrea Guidolin. So we believe that there is stability in the sense of the values, not in the sense of the position of the cell.
Thank you.
Yeah, you're welcome.
I mean, I have one in relation to what you were just mentioning, Claudia. You were saying also at the end of your talk that you're thinking of a way of incorporating these as cells into a possible definition of a distance. And
yeah, on the one hand, and I had hoped to present this today, but we were not ready with Asilata, Robyn, Barbara, and Celia. By the way, this is a research group that was born during the last Women in Computational Topology meeting. We are trying to use critical cells to describe better the matching distance, in the sense that we believe, but we do not have the proof, that we believe that the matching distance is always realized by lines. So the matching distance is defined, let's say between two persistence module is the supremum varying all lines of some weight that depends on the line, which is based on the slope of the line, and then the bottleneck distance times the bottleneck distance between the restriction of M to L and the restriction of N to L. And so here we need to consider all possible lines, but we think that it is sufficient when we have C bar, so it should be closed with respect to, okay, to respect to the list upper bound, to consider lines through two critical values, or to consider diagonal lines through one value. But again, we have not yet the complete result, so I didn't present it. And another thing, this is done, a student from Middle East Technical University in Ankara is studying, yes, is to define the new distances for persistence modules, always defined using slicing with the lines. But in that case, in reality, critical values do not play an important role, because he's considering rectangle modules, and so basically it's the rectangle, the coordinates of the corners of the rectangle that plays a role. And so
thank you.